Okay, this is video 1 in the week 7 homework series videos for grade 11 university math. So we've started a new strand, which is strand B, and it's all about exponential functions. So right now we're on B1, which is representing exponential functions. So topic we're going to look at graphs of exponential functions and exponent laws and rational exponents. So this video is just on graphing exponential functions and looking at their key features. So we're starting with this graph. So first things first, how do we recognize an exponential function? Well, it turns out all their equations are going to have an x in the exponent. So they'll be like some number 2 to the power of x. As long as there's an x in the exponent, it's an exponential function. Or if we had y equals even like a half to the power of x, even multiple things like 3 times 2 to the power of x plus 5. There's still an x in the exponent, so all of these things are considered exponential functions, and we're going to learn how to graph all of them. But we're going to start with the basics. So we're going to start with just graphing f of x equals 2 to the power of x. So we've got a base and we're going to see what that graph looks like. So I'm going to make a table of values. So I'm just going to pick random numbers of values of x, like -2, -1, 0, 1, 2, 3. And I'm going to plug those numbers into my equation. So f of -2 would equal 2 to the power of -2. And since I remember exponent laws, I know that's actually 1 over 2 squared, which is 1/4. Or if you just plugged it in your calculator, it would have told you 0.25. And if you continue doing that, if I plug in -1, I'll get a half, or 0.5. If I plug in 0, 2 to the power of 0 is 1. 2 to the power of 1 is 2. 2 to the power of 2 is 4. And 2 to the power of 3 is 8. So now I've got all of my values. I'm going to graph it. So when x is -2, y is 1/4. Then we got a half, 1, 2... 4, 5, 6, 7, 8. So that's what it looks like. And it turns out our function actually just approaches the x-axis here. And then it gets super steep on this side. So let's point out some key features of our exponential function. So what we have is we've got an asymptote right along this line right here, right along the x-axis. And how I'm going to describe that is I'm going to say we've got a horizontal asymptote. A horizontal asymptote at, I'm going to say it's at y is equal to 0. Because if you notice, it goes right through 0 and all the way along this line, y is equal to 0. So that's how we describe a horizontal line. We always call it y equals something. So in this case, 0. So it's an asymptote because our function is approaching it, but it will never reach 0. And we would know that because 2 to the power of x can never equal 0. Like there's no number you could sub in for x that would make that equation equal. If you plug in 0, it equals 1. If you plug in 1, it equals 2. If you plug in -1, it equals a half. So like you're never getting to 0. So that's why we have an asymptote there. Other key features that we have a y-intercept, and our y-intercept is 1. Another thing that we can notice is as we go along the domain from left to right, like if you look at all of these x values and what's happening to our function, as we move from left to right, our graph is increasing. It's like its slope is increasing. It's like a pretty horizontal line here, and then it's getting steeper and steeper and steeper and steeper. So our slope is getting bigger. Also, our y values are getting bigger. So we would say this is an increasing function. And we would also say that we could also use the word exponential growth to represent this function. So certain biology things are represented with this function, like bacteria doubling over time would be an example of exponential growth. And if we wanted to describe the domain and range of this graph, The domain is going to be x is an element of the set of real numbers, because x can be anything. Whereas the range, as we can see by our asymptote, y has to be greater than 0. It's never going to be down here anywhere. Okay, let's try another one. So let's try a fraction guy. F of x equals 1/2 to the power of x. So I'm going to sub in some values for x into my equation and solve for y. So if I sub in a -3, I get 1/2 to the power of -3. And I know my negative exponent thing tells me I can flip my base and make my exponent positive. So what I have is 2 to the power of 3, which is 8. I'm going to do the same thing for all these values, and this is what I get. So pretty much the opposite of the other one we just did. So when we're at -3, we're at 1, 2, 3, 4, 5, 6, 7, 8. Here, we're at -2, we're at 4. -1 is 2. 0 is 1. 1.5. 1/4. So there's our exponential function. So yet again, we've got our horizontal asymptote at y equals 0. We've still got a y-intercept at 1. Our function this time is decreasing. So as we move from left to right along the domain, our function's going down, the negative slope. It's starting off with a super steep slope, and then it's getting less and less and less. So it's decreasing. Also, we could call this exponential decay. And again, in science, certain radioactive isotopes would follow this function's pattern, where it would decay over time, like things like half-life, if you've heard of that, would follow this pattern. And the domain and range will be the exact same for this one as it was for the other one. So you can give these a try if you want. Make sure you understand it. Try ones like, what would 3 to the power of x look like? Or what would 10 to the power of x look like? Maybe graph them on the same grid so you can see what the difference would be. And what about if you did like 1/4 to the power of x? Or a super small number like a 1/10 to the power of x. So give those a try. Check out what your key features would be and what your graphs would look like.